So we were looking into transponders, right, as one of your friends suggested. And today we will be looking closely into the antenna subsystem. Okay. So the antennas are carried on the satellite, which provide dual functions, which is nothing but receiving as well as transmitting. So which means it is uplink and downlink. So uplink is to actually transmit information from the base station, okay, and downlink for transmitting the signals from the satellite. So your antenna should be in such a way that they are capable of handling things, and it should be as sensitive as possible. Okay. The range from dipole type antennas where omnidirectional characteristics are required to be highly directional antennas required for telecommunication purposes and TV relay and broadcast. Okay, so not only for the purpose of communication, but also for the purpose of entertainment, antennas are employed. Your directional beams are usually produced by means of reflector type antennas. Okay, so those antennas, the dish that you see, okay, is the reflector type antenna, and the paraboloid reflector being the most common. So the ones that you see normally, okay, in your antennas, in your dish. So the gain, okay, the gain of the reflector, the parabolic reflector, is nothing but given by G is equal to Ni pi d divided by lambda the whole square. So as we all know, lambda is nothing but the wavelength of the signal. So which means from the crest, from the highs to the lows, okay, in the waveform. And d is the reflector diameter, as to how big is your reflector. So that is your d. And NL is the aperture efficiency, how efficient it is able to communicate. So these, most of the things are standard values, and some of them will be given in the problems. A typical value is about 0.55. See, as I mentioned, okay, it's about 0.55. The 3 dB beam width is given by, so if I take 3 dB into consideration, okay, to stabilize things, when I take 3 dB, so that's approximately about 70 into lambda divided by d degrees. So when in the question 3 dB is mentioned, then you will have to use this value. So you will have to substitute the wavelength value and the diameter of your antenna. So the ratio d by lambda is the key factor. Okay. So this d by lambda is going to be the main factor as to how things are going to work out for your antenna. Okay. So you will have to know how much is your wavelength, and you will have to know how much is the diameter for your reflector. Okay, so these are the key points. The gain being directly proportional to d by lambda the whole square, and beam width inversely proportional to d by lambda. So the gain is directly proportional, okay, and your beam width, okay, that is your theta 3 dB, is actually inversely proportional. So which means d is at the denominator and lambda is at the numerator. In comparing C band and Ku band, the largest reflectors are those for 6.4 gigahertz uplink downlink. Okay, okay, so as we were seeing, your beam width is inversely proportional and your gain is directly proportional to d by lambda. Okay, so as I was mentioning, your uplink frequencies will be higher than your downlink frequencies because it takes a lot of effort for the signal to actually pass through and go and hit the required antenna in space. But for the downlink, it's relatively comparatively lesser frequency will actually work out. Comparable performance can be obtained with a considerably smaller reflectors in the 1412 gigahertz bandwidth. Okay, so if we consider this 1412 gigahertz bandwidth, then it is going to be smaller reflectors. So as your frequency increases, your reflectors become small. If your reflectors are bigger, then your frequencies are lesser. Okay, so that's inversely proportional. Satellites used for mobile services in the L band employ much higher antennas, much larger antennas in fact. So those which are in the L band. So the reflector areas are 100 meters square to 200 meters square. So which means as your frequency reduces, your antenna's size will start increasing. Okay. So this is a typical view of how your antenna structure is. Okay, you can see that it's a complex structure. Okay, it's a complex structure where it has reflectors. Okay, then it has your horn-like structures. Okay, which are used for even receiving signals and transmitting signals. Okay, and yeah, so these are the individual horn structures. This that you see here, okay, individually it is shown here, and structural cover. Okay, switch drive motor. So the motor has to actually rotate the antenna. Remember, we have motors, we have sensors. So accordingly, as per the signal, we can actually move the direction of the antenna. Why we need to change the direction of the antenna? So that reception and transmission becomes proper. Okay, so I cannot say that once I set here and then send it to space, it will be all fine. No, even though it travels a long distance, okay, even though we set it right here, but still due to the network, the the environment there, the atmosphere here, the harsh environment there, what's going to happen? Or it's all going to be misplaced. So when I say misplaced, they are going to lose its optimal working positions. So with the help of these motors, okay, with the help of these motors, I will be able to move the antennas in such a way that they transmit and receive properly. Okay, so this is the front view of the same antenna, where the transmit feed, the receive feed, okay, and the reflector. Why do we use reflector? So that signals are not lost. Okay, so that it is properly communicated, properly transmitted. Then this is talking about the diameter. Okay, reflector diameter and the focal length. So all this actually plays a very major role. And this is the coverage of your antennas. Okay, northwest zone, northeast zone, southwest and southeast. So each antenna will take care of different zones. Okay, so as you as your frequency increases, okay, you can see that the diameter is actually reducing, the antenna diameter. Okay, so here your frequency is lower, so your reflector diameter has actually increased substantially. Okay, so we have few regions based on the oceans. Okay, and we have seen this in our initial classes also, right? The Atlantic Ocean region, the Indian Ocean region, the Pacific Ocean region. So this figure that we saw previously was the antenna subsystem for Intelsat 6. Okay, for Intelsat 6. And it covers these three regions. Okay, provides good illustration of level of complexity which has been reached in large communication satellites. So this is the level of complexity involved. Okay, reflector diameters and how it should be positioned, what are the horns and how are the motors, and what regions it's been covering. Okay. The largest reflectors are for 6.4 gigahertz, okay, because the frequency is a little lower, so the reflectors are to be larger. If the frequency is too high, then as we saw previously, your diameter will get reduced. These are fed from horn arrays, and various groups of horns can be excited to produce the beam shape required. So we can move around and we can make sure that we get proper signals. As can be seen, separate arrays are used for transmit and receive. Each array has 146 dual polarization horns, and in 1411 gigahertz band, the circular reflectors are used to provide spot beams. Spot beams, just like a laser spot, one for east and one for west. As in figure, these beams are fully steerable. Okay, so which means it can move around due to the motors that are involved. Each spot is fed by a single horn, which is used for both transmit as well as receive. Okay, so you will have both transmit as well as receive. So you can see based on this regions, okay, the ocean regions, as to how much they will be able to cover. Okay, so the plain ones that you see, the bigger one is your 6.4 gigahertz, and slightly dotted one is your 6.4 gigahertz one, which is cross polarization, and your 1411. Okay, so as your frequency increases, the coverage also does decrease. Okay, the coverage decreases. You can see that it's just covering a small area. Okay, so this is for your Intelsat 5, the previous version of your Intelsat. Okay, and this antennas that you saw here was for the version 6 of Intelsat. Okay, so this is the coverage map, how the signals are covered. Okay, satellite transmit capabilities. Note that 1411 gigahertz spot beams are steerable. Okay, so we call it spot because it is looking like a small circle and it is steerable, which means I can bring this spot here, I can bring this spot here, and this spot can be brought here. So anywhere. So it is just like moving a torch, right? So signals, the tracking can happen at any designated area. Okay, so we can. This is the best advantage, of having a satellite. That's why countries actually invest a lot of time in building satellites, wherein it is an extra eye. Okay, it's an additional information that they get, right from space, where they can have detailed information. So these spots can actually move, okay, from left to right and from top to bottom. So it's in the shape of a circle, small circle. So it's called a spot beam. Wide beams for global coverage, as I showed here. Okay, these are wide beams, so it can cover a large area, and the spot beams can cover smaller areas. This horn beam signal directly to the earth without the use of reflectors. Okay. As shown in figure, a simple bioconical dipole antenna is used for tracking and controlling signals. So bioconical dipole antenna is here. I'll show you. Yeah, here. So this is biocone dipole antenna. Okay. So just look at it. Fine. A simple bioconical conical dipole antenna is used for tracking and control the signals. Okay. The complete antenna platform and the communications payload are despun to keep the antennas pointing to their correct locations. Now this is very important. Okay, so if I'm just covering the ocean and I'm not covering the land area, there's no point, right? So I should be covering the land area wherein the countries, the continents are covered. So that's the reason of having motors and movable antennas. Okay. The same feed horn may be used to transmit and receive signals or carriers with the same polarization. So if you're using a circular polarization with your transmitter, the receiver also should use the same kind of polarization. You cannot have two different types from the transmitter and receiver. And these transmit and receive signals are separated by something called diplexer. Okay, diplexer, and the suppression is further aided by the means of frequency filtering, just like how we saw transponders. Okay, how they are, we have about 12 transponders, and for the guard band we use 4, and then the data we use 36, totaling to 40, right? So similarly, these kind of separations happen, and we will be able to work on it. Okay, your polarization discrimination also may be used to separate the transmit and receive signals using the same feed horn. Okay, for example, the horn may be used to transmit horizontally polarized waves. Horn is nothing but the antenna feed. Okay, the antenna feed. The waves in the downlink frequency band while simultaneously receiving vertical polarized waves in the uplink frequency band. So it can transmit and receive at the same time, just like your duplex communication. So in simplex, it has to wait either to send or to receive, it has to wait, right? But in duplex, sending and receiving can happen at the same time. So duplex is it's a complex way of communicating than your simplex communication. The polarization separation takes place and in a device which is known as couplers. Okay, so these are called as orthocouplers or orthogonal mode transducer. So this will help us in deciding as to what kind of polarization we need to take up. Do we need to take up circular? Do we need to take up vertical? Or do we need to take up horizontal? Separate horns may also be used for the transmit and receive functions with both horns using the same reflector. Now that's the advantage. You can transmit or it can be received using the same reflector. Now that's an advantage. So we try to employ these kind of things, which can be used multi-purpose. We just do not employ things just for one functionality. Okay, so we will be now starting into something called space link. So we have right now seen with communications that are happening at the power supply units, okay, altitude control, then thermal, TTNC transponders, then the antenna subsystem. So right now we will be looking at the transmission side. Okay, so in order to transmit these signals, what are the requirements? So here the link power budget calculations are made. So this is very important. Okay, link and power budget. So here you will also be looking into something called your isotropic EIRP, equivalent isotropic radiated power. So that concept also comes here when we discuss about the space link. These calculations basically relate to two quantities, the transmit power and the receiving power. So ultimately, once we know P in and P out, so we can use the graph and find out where is the saturated point. And once we have the saturated point, we can back off the input and we can back off the output in such a way that I get the linearity wave. Okay, so I think you remember, right, yesterday's class where we discussed we are interested in looking at the linear curve. Okay, we do not want it to move into saturation and be stable. No, we want it to be exponential. We want it to be, this is our region of interest. This linearity is our region of interest. We use square brackets to denote decibel quantities. Keep in mind, okay, we are going to use some notations here. Okay. Link budget calculations are usually made using dB or decilog quantities, and square brackets are used to denote this dB. So whenever you find something inside the square bracket, it is understood that the values are in dB. Keep this in mind and make note of this point. Where no ambiguity arises regarding the units, the abbreviation dB is used. Okay, so square brackets, when it's used, then it denotes your decibel quantities of using the basic power definition. So power dB in bracket. For example, the Boltzmann constant is given as 2 to 8.6 dB. Although strictly speaking, this should be 2 to 8.6 decilogs relative to 1 joule per Kelvin. Right. So some constants you will have to remember, okay, and some will be directly given in your question paper. Where it is desirable to show the reference unit, this is indicated in the abbreviation. For example, if I use dB hertz, okay, this means it is in decibel, but relating to 1 hertz. So you can see dB Hz. So it means it is the factor of a decibel and hertz with reference to 1 hertz. So here now again, when we talk of this Boltzmann constant, okay, it talks of 1 joule per Kelvin. So some of the basics that you'll have to remember with respect to antennas. Okay, so I hope you have understood the introductory part, right, as to what all we will be looking into and what is actually expected and how are the notations. And we will look into the basics of antenna in our next slide. So these are some of the basics of your antenna. Okay, and your antennas are broadly classified based on its functionality. So either it can be transmitting signals or it can be receiving signals. Accordingly, they are called transmitting antennas and receiving antennas. Okay, so although the requirements for each function or mode of operation are marked different, a single antenna may be and frequently is used for both the functions at the same time. Okay, so as I was mentioning, we do not want a single performing device. Okay, we want a single device to perform multiple operations. Another way in which antennas for use in satellite communications can be classified is into earth station antennas and satellite or spacecraft antennas. Okay, so those antennas that are used in base station and those that are used in the spacecraft. So this is another type of classification that can be done. So one is based on either if they're transmitting or receiving, so that is one classification, and the other one is where the antenna is located. Is it located in the space? So it's called a space antenna or satellite antennas. And if it's located in the base station, then it's called an earth station antenna. Although the general capabilities or principles of antennas may apply to each type, the constraints set by physical environment lead to quite different designs in each case. Okay, so this is nothing but your radiated power. Okay, so transmitted, so your total power, you have your feeder, okay, then your source, then your radiated power, then at your receiver, okay, you will have PM wave. Okay, so you will have your received power in feeder, and the total received power, and finally it will get into the receiver. So from here it gets transmitted and from here it gets received. So this is a simple representation of your transmitting and receiving antenna. So in the A figure, okay, we saw a transmitter, and in the B figure we saw a receiver. The power amplifier in the transmitter is shown as generating PT, okay, W. A feeder connects this to the antenna, and the net power reaching the antenna will be PT, which is total power minus the loss in the feeder. Okay, so whatever power is here, so that will get minused with the feeder loss. Okay, so power, certain amount of power is getting absorbed by the feeder. These losses include ohmic losses and mismatch losses. So it can either be ohmic losses or it can be your mismatch losses. So mismatch will happen when there is improper impedances at the transmitter and receiver side. Okay, so that actually plays a very major role. Okay. The power will further be reduced by losses in the antenna, so that the power radiated, okay, P rad, is less than generated at the transmitter. So that's important, isn't it? So radiated power and your received power wouldn't be the same. The antenna as a receiver shown in B, where PREC is transferred to the antenna from passing radio wave. So these radio waves will actually pass through, okay, and it will get into your receiver. Okay. And these losses that you see, the antennas will reduce the power available for the feeder. So again, there is feeder. Here you will see feeder. So feeder is again involved here. So ultimately, PT and PR will be drastically different. The receiver feeder losses will further reduce the power, so that the amount PR reaching the receiver is less than that for the transmitted antennas. Right? Okay. So we have certain standard equations. Okay, so we will be just looking into the slide, and probably if time permits, then we will even look at your EIRP. Okay, so that's also an important concept. And yeah, so referring back to these diagrams, okay, your radiated power is actually equal to PS. So now let's get back to this. So you can see your radiated power is equal to PS. So this PS is not equal to PT because of the feeder. So there will be mismatch losses, there will be feeder losses. So those losses minus PT, okay, PT minus those losses will be equal to PS. So here PS and P radiated power will be the same. Okay. By imagining the isotropic radiator to be at the center of sphere of radius r, the flux density, okay, that is your psi, okay, which will actually flow into the area, is given by PS divided by 4 pi r square. So 4 pi r square is a standard form, okay. So this is the general equation that you have to remember for the isotropic radiator. Then the flux density from a real antenna will vary with direction. So your flux, that is your fields, will vary as the direction of your antenna does change. Okay, so it is always of greater interest for us to keep the antennas in such position where it receives and transmits proper signals. The flux density of real antenna will vary with the direction, But with most antennas, a well-defined maximum occurs. So we know, okay, we know as to which is going to be maximum and which is going to be minimum based on how we have placed it. The gain of the antenna is the ratio, okay, the ratio of the maximum uh, to that for the isotropic radiator. So the maximum flux that it can actually generate and to the isotropic flux, okay, to the isotropic flux that is actually practical. So I can say that, you know, this is our theory part, okay, your phi m is your theory part, and your, sorry, your psi I is your practical value. Right. So another important concept that we will be looking onto here is your EIRP, which is also called as equivalent isotropic radiated power. So I think you would have seen these concepts, you know, in your wireless communication labs as well, right? Wherein extensively we will be discussing about this in your algorithms, in your path loss experiments. Okay, it can be your Okumura or your Kata model. A key parameter in link budget calculations is EIRP, okay, and it is denoted in short as EIRP. The maximum flux density. Okay, now what is psi m? Psi m is nothing but your GPS divided by 4 pi r square. Okay, where G is nothing but the gain of the antenna, and we know the gain was given in the previous section, right? This is your gain, right? So all the formulas, so what I advise you all is, you know, just make a note of all the formulas so that these are connecting to each other, and we will be using them one after the other and substituting them one after the other, and it becomes easy for you to understand them. So gain, you know, gain, we will be using this, okay? So this is the gain with respect to your space length, and that gain was exclusively for your antennas. Okay. So isotropic radiator with an input power equal to GPS, okay, this one, would produce the same flux density. Hence, this product is referred to as EIRP, or EIRP is referred in decibels relative to 1 watt or decibel watt. So this is a reference to 1 watt. Okay, so your EIRP is equal to your GPS. So gain into PS. Now, why are we talking about gain and PS? See, PS is here. I will be giving a gain. Okay, so that will actually give my EIRP. So your equivalent isotropic radiated, uh, you know, functionality. So this PS is multiplied with the gain. Why gain? Because it had a loss because of the feeder. So losses happened. So PT minus loss. So that loss is nothing but your feeder loss. Okay. So that if in case we consider your source, okay, your PS, okay, to be in watts, then EIRP, this is going to be your formula. EIRP is equal to PS plus G dB watts. So dB with reference to 1 watt, where PS is also in dB watt and G is in dB, okay, in decibels. So isotropic means rather loosely, equally in all directions. Okay, so based on this, we even have a formula, simple numerical implementation of EIRP. An isotropic radiator is one which radiates equally in all directions. Now we need this kind because we are dealing with signals coming from a very far distance, right? So we just do not want to use spot beams, but rather we like to use beams which cover more area in our planet. Okay, previously we have seen that, right? The map coverage. I think you can recall that, the map coverage by each year. So I am interested in looking at, you know, this pattern. Okay, when I say this pattern, the coverage of the antenna should be high. So if my coverage is high, then I don't have to move it around, and the life of the antenna, the motor, will increase if it's used less. Okay, so that is also one thing, one important parameter to keep in mind. No real antenna can radiate equally in all directions. So practically, we cannot find that 100% 360-degree it is radiating signals, efficiently. But there will be some practical issues. It does, however, provide a very useful theoretical standard against which real antennas can be compared. Okay, so I set a high standard, which is 100%, but then I may not be able to achieve 100, maybe 90, 85. If I reach, that's going to be the best value. You can recall this dish antennas, when the service engineer comes and installs, he will include, okay, he will set up the wire with his device and check for the level of percentage of receiving signals. So if he finds that it's above 90, then that's the max. So which means the remaining 10 are all the losses because of the atmosphere. Okay, so 100% we cannot expect signals to reach our base station. It can be made 100% efficient, meaning that it radiates all the power fed into it. So that is impractical. So let us look into a small problem here, okay, where downlink is at 12 gigahertz, and it is with a transmitting power, okay, of about your PT. Okay, transmitting power is about 6 watts, and the antenna gain is 48.2 dB. Calculate the EIRP. So what was the formula for EIRP? EIRP is this. Okay, so 10 log, okay, 6 divided by 1. Why? Because it's in dB, and I want to put it in a different values. This is only in dB, this is in dB watt, right? Okay, and the 6 watt is again different. It's in a different form, so I'll be using 10 log form, and I'll be converting it into a dB W form, dB watt form. So I'll be referencing, or I will be dividing it with reference to 1 watt. So once I do that with the help of log, I can convert it from your dB to dB watt. So 10 log plus your gain. Okay, so whatever value you get here, you add it with 48.2. So this is going to be your final EIRP. Okay, yeah. So your PS, okay, your PS. So EIRP here is equal to your gain into PS. So EIRP, if I see in watts, so it was mentioned in watts, right? So I will use PS plus gain. So that gives my final value here. So there are a few more simple problems that we can actually look into. Yeah, just another 2 more slides, and then we'll conclude this class. For a parabolic antenna, the isotropic gain is given by this equation. Okay, so you should check what kind of the other idea that I will give you is based on the inputs given in the question. Okay, you can actually decide which formula you're going to use. Okay, either you're going to use gain this formula, or you're going to use gain is equal to this. Okay, here also you can see that your gain is equal to psi m divided by psi I, right? So you can actually make the best use, and you can identify, okay, based on the values as to which formula you're going to use. So those values given in your problem is going to play a key role. Okay, so in case of parabolic antennas, the gain is given by eta 10.472 f into t square, where f is nothing but your frequency of your carrier signal, and this is all in gigahertz, remember. And d, as you all know, is the antenna's the reflector's diameter. Okay, and in meters, and eta is the aperture efficiency. So we saw it was about 0.55, right? Yeah. So although the values are as high as 0.73, sometimes, sometimes it can go up to even 0.73. With diameter d in feet and all other quantities as before the equation, then, so if in case the diameter is mentioned in feet, okay, then your value of gain also does change. It becomes 3.192 f into d. So d is your diameter for your antenna, f is your carrier frequency. So you can see that the number here, okay, the fractional number here changes based on what kind of antenna that is being employed. Okay, so we will just look into this simple problem here. Calculate the gain in decibels of a 3-meter parabolic antenna. So here they have mentioned, okay, so as to what kind of antenna it is, and it's operating at 12 gigahertz, and assume eta is equal to so much. So most of the things will be given. The only thing that you have to do is just extract value, know which type of formula to substitute, and you can just calculate. So we are using this formula here because it's a parabolic antenna, right? So G is equal to 0.55 because eta is given here. Then we have the constant value 10.47 into 12. What is this 12? This is the frequency. And then D. So D is nothing but your 3 meter. Okay, so just substitute and you will get this value. And if in case you want to mention it in terms of dB, then 10 log the value of your gain, so that will actually convert it in the form of dB. So students, any doubts here in the concepts that we have discussed so far?
No, sir.
Okay, fine. So we will try and continue, okay, with the next concepts available, which will be transmission loss in our next class.